Hello there, everyone. So this is the first part of the week 4 notes, and you actually should be getting this either in class or synchronously this week. But just in case either you weren't able to attend class or you want to come back and just review, I'm going to put this video together real quick of this set of notes. So to recap where we're at, we're talking about the atomic theory and the history of it. We're currently with Bohr's model, and we're using examples like the SALT demonstration of ground state and excited state in these orbits, as well as the flame test lab, again relating ground state and excited state and some of these ideas of orbits and that electrons can exist at very specific distances and energies. So this is the Bohr model. We're going to move on from that just a little bit here with the quantum model. So quantum model is going to be based off of quantum theory, and the idea is that electrons exist at specific energy states. And as you're following along, this so far sounds pretty similar to the Bohr model, and you're correct at this point. And again, if you think about the flame test lab in particular, if we have an electron at a very specific energy and distance, if it absorbs energy, it can move to an excited state, meaning it's further from the nucleus with greater amount of energy. But that's unstable. And so if it releases that energy in the form of a photon, then that electron is allowed to move back down to its original ground state. So if it absorbs energy, the only way it can move back down is by releasing that energy. And at least in our lab, as we were observing the flame colors, you were seeing a bunch of photons. So as you start to think about light, if you look at any light source around you right now, really what is happening is a bunch of photons with specific energies are reaching your eye and exciting your nerves and the rods and cones in your eye, and pretty much your eye is telling your brain to see a certain color. So that's how we want to start to think about light, is that these photons being released because electrons are moving from the excited state where they're unstable back down to a ground state. And again, the idea is that these energy states are fixed, which is a little bit of a weird idea. But if we look at this kind of stair analogy here, if I've got an electron here at the ground state, depending on how much energy it absorbs, it can move up to higher excited states. So the more energy it's able to absorb, that very specific amount of energy can get it to different excited states. But the idea is, let's say just this second energy state, if it's going to be able to move up into that energy state, meaning it's got greater energy and it's further from the nucleus, it's got to absorb a very specific amount of energy. If it does not absorb that correct amount of energy, it can't exist at this higher energy level. So it's almost like floors of a hotel. You exist either on the first floor or the second floor, but you don't exist in your bed or something in between. And that's kind of what we're trying to say here. Another last analogy to this idea of quantum, where we have very specific energy states, is maybe a ladder. And again, if you're trying to move your foot up from this rung to an excited state, if you will, you have to add the perfect amount of energy to get your foot up onto this rung. If you only add this much energy, you're coming back down to the original step. And so that's the idea of why these electrons can only exist at specific energies and distances from the nucleus. And so when we talk about these photons being released from excited state back down to ground state electrons, what we're actually talking about is electromagnetic radiation. And these are waves of oscillating electric and magnetic fields. And you don't have to memorize this isn't in red, but you'll see as we move forward, the idea of waves is going to be very important within the quantum model. And so I just wanted to bring that up. The other reason to bring up electromagnetic radiation is if you look at the spectrum of electromagnetic radiation, you'll see some things like radio waves or microwaves that you're probably used to, but the visible light is part of that spectrum. And as we move from red to violet, we are increasing the energy of the photons that are interacting with our eyes. And so I mentioned this in the previous lecture, but this was one of the questions that we wanted you to think through. So I believe potassium as an ion was a violet color. And so the potassium, when that ground state, excited state movement happened, those photons were the most energetic, reaching your eyes. So in general, we increase energy. And it's also just interesting to point out that something like radio waves are really, they're photons moving at the speed of light. Again, all of these are photons moving at the speed of light, but the radio waves are just really slow light waves. So it's just kind of an interesting aspect to electromagnetic radiation. So up to this point, it might kind of sound like, well, we really haven't done much to move on from Bohr's model here. And so that's what we're going to establish next. So remember, he's saying that electrons exist at very specific distances and energies. And we have the planetary model, meaning we can predict where electrons would be, just like planets and the moon. We can predict which planets will be in our view at night because we can predict their orbits. And so what happens, and then actually a number of scientists before Schrodinger, but Schrodinger has this cat idea. And so this is a thought experiment. Again, at least I hope he didn't carry this out because it's kind of messed up. The idea is you have a box, can't see in it, can't hear, know nothing of what's going on in the box. We put a cat in there, and then we also have a radioactive trigger. And ultimately what we're saying with that is a 50-50 chance if decay occurs. So we don't know. We can't trigger it ourselves. It's totally chance, 50-50 chance. If it triggers, then the hammer is going to fall. It's going to break that vial of poison, and it's going to kill the cat. But Schrodinger's point was, if we don't have evidence within knowing either that the trigger went or that the cat's dead or alive, then because we don't have any evidence and because we can't see inside this box, then the cat is both dead and alive at the same time. And so this is the Schrodinger's cat experiment, thought experiment, and it's famous because what it does is it leads towards this idea of electrons being treated as waves. So this is why I brought up electromagnetic radiation. And so what Schrodinger does, not just through his thought experiment, but through a lot of math, is he starts to talk about, well, electrons travel in these orbital clouds, general shapes. So you can see some of those shapes over here, and we will work with these and look at them. But he's also saying we can't pinpoint the location, and this is where the Bohr model breaks down. Because Bohr's model did really well with small atoms like hydrogen with 1 proton and 1 electron. As we add more electrons and protons, his models doesn't really fit the data and observations that we see over many, many years of the work. Now, this cloud model is a little hard to describe, and so I'll give you a couple of analogies. One, if you think about this fan blade on the left, if it's not moving, we know exactly where those blades are located. But when we turn them on and they're moving quickly, just like electrons are moving extremely quickly at the speed of light, we start to kind of you can't pinpoint the location. So if you look to the right here, we have a general idea of where that fan blade is, at least when we took this snapshot. But is it possible that the fan blade's a little over here or down here as it moves through? Yes. So really, if you kind of think about this image, those orbital clouds represent generally where we would predict the electrons to be, but not all the time. All right, hopefully you have some room in your notes here. This is Schrodinger's wave equation where he came up with those. And I'm just kidding. I don't know what half of this stuff actually means. I just wanted to point out that there's a lot of math. Like, people spent their lives going through this math to get these images and these pictures and shapes that you're going to eventually see for these orbitals. So they didn't just make it up, but it's also way beyond the scope of this class. So something else that's going to kind of play into our vision of electrons is the duality of light. And so this is a famous experiment called the double slit experiment. Einstein was involved with photons and the duality of light. But really what we're trying to show you here is if light behaved as a particle, then you might get a photon that gets straight through that slit, but then it would just bounce around and likely just bounce back through the original slit. Maybe it bounces around and eventually somehow gets through the second slit. But the idea is that when you perform this experiment, you can see the light come through this last slit down here, these 3. And if light was a particle, then it would be very hard for a particle to somehow make its way consistently through, and yet it does, but it flashes. And so this experiment kind of led scientists to understand that light can behave in certain situations as a particle, but also can behave as a wave. And the reason I bring this up is because it's further on after this, electrons behave in a similar way. So because electrons can behave as both particles, because again, they have mass, it's not much, but electrons do have mass and they have a charge, so they're not photons, as we're saying here, but they do behave in terms of this example as both particles and waves, and it helps explain the quantum model. So that leads us to the second scientist we're associating with the quantum model, and that is Heisenberg. And what he's able to determine is that it's impossible to determine both the position and velocity of an electron. And so again, it's that idea of duality of both a particle and a wave behavior. So that's why we have these orbital clouds with weird shapes, because generally we expect the electrons to exist within those shapes. And I don't know if Breaking Bad is still a thing out there, but it might make sense why that character was named Heisenberg based on the duality. Is he a good guy? Is he a bad guy? Anyway, if you have watched Breaking Bad, and you should, then this makes sense. If not, I will move on from my nerdy little TV thing here. So let's wrap up the quantum model, because this is really at current understanding, current model. You'll see it called a bunch of different things. I'm just going to try to simplify it and call it quantum model. Number of different scientists were involved in this. But ultimately, with this quantum model, take-home point is that we never know for certain where an electron is. But we have equations, you saw them, and we're able to predict the probability, or predict generally where an electron is going to exist with a certain distance from the nucleus. But again, given the duality nature of electrons and their movement as waves, we cannot pinpoint exactly like Bohr's model was imploring us to do. So let's just double check where we're at with this. So which statement describes a concept included in the wave mechanical model? So again, wave mechanical, as mentioned, is same thing as quantum. So the idea of wave. And you'll see wave mechanical some places too. And it's one of those just annoying, goofy chemistry things that we have multiple ways of describing the same thing. If you read through the bottom there, though, if you want to pause, this would be a good one to pause for. So which of those would describe the quantum model? It's D. And you need to be careful, because here, this sounds pretty good, but this is really the Bohr model, and we know that electrons do not orbit, and they're not at fixed distances. So they generally are a certain distance with a certain energy, but again, we cannot pinpoint, we cannot predict, and so they don't orbit. So D becomes our correct answer. And again, you'll notice in that image, we have a majority in this orbital. We'll talk about this as an s orbital. We'll talk about that in a moment. 90-ish% of the time, we would anticipate that the electron is within this shape at a certain distance from the nucleus. But you'll notice once in a while, the electron could exist just briefly outside of that orbital. So that is where we are with the quantum mechanical model. The last thing I'm going to try to do, and again, it's hard to describe movement of electrons, especially as waves, but maybe one last way, and this is just kind of cool anyway, is that birds and murmurations kind of behave like flying magnets. And if you think about electrons behaving as particles and waves, but they do have a charge and they do have mass, they're going to repel each other. And so one of the things that we'll move into is electrons are going to fill in around a nucleus very specifically. And there's a reason for that, because they repel each other. A lot of the math that in those equations that you saw but didn't actually have to write down has to do with that repulsion and how can we fit electrons, how are they going to interact with each other. And so one way to maybe, if we had a bunch of electrons, obviously there's more electrons than would ever exist around any of the atoms that we're aware of. Notice how we have individual birds, kind of like particles, but they're behaving almost as a wave. And again, this isn't exactly, I don't want you to think about this as what electrons look like, but this idea of kind of particles behaving as waves and repelling each other is kind of the idea of what's going on around a nucleus with those electrons in those orbital clouds. So to wrap up our model of the atom, we have just a solid sphere. That was Greek and Dalton. We get the plum pudding model with the discovery of the electron. Again, Rutherford's talking about a lot of empty space, but we're not sure how those electrons are moving within the empty space. The Bohr model, which was, again, the popular model for all of you to draw out when I ask you to make your own version of an atom. But again, they don't orbit. We can't predict. And so that leaves us with the quantum model, which is, again, this cloud of probability where an electron should exist. And just to wrap this up, remember we've talked a lot about models changing over time, and this is, I think, a great example in chemistry specifically, where as more and more technology and evidence and experiments were happening, we built and continued to change the model. And this is really a great example of how science works. Okay, so now that we've got an idea of our current model of what an atom looks like and the behavior of electrons around the nucleus, we can start to talk about how do those electrons configure themselves as they fill in further and further away from the nucleus. By the way, that's a pretty good chemistry cat joke right there. Okay, so let's review just really quick, bring home the idea of the flame test lab. So remember that we have electrons existing in very specific energy levels. And if they were to absorb some energy, and again, the right amount of energy, they can move up to higher levels. And it doesn't have to be just one level at a time. If it's the correct amount of energy to get into 2 levels up, then it will do that. Now, it doesn't move like that. It's not this continuous energy. It's a quantum jump. So either the electron exists in its ground state or it exists in the excited state. And there's no in between, just like floors in a hotel. Now remember that at this point, in the excited state, the electron is not stable, and the electron is going to try to move back down to its ground state, but it has to release the energy absorbed to do that. And depending on where it is in its excited state, it may release that amount of energy, which was just jumping down from the 3rd to the 2nd energy level. Say instead its excited state is even further up in the 4th energy level, and it releases energy to move back down to the 2nd level, and notice that was a different color of light. So this is why we're getting unique light being produced by different metal ions in the flame test lab, at least, because they all have unique electron configurations. And you're seeing a combination of all of those unique ground state, excited state movements. We remember, because right there I was kind of showing you the Bohr model. We were predicting exactly where those electrons resided, and that's not how it works. Remember that with the quantum model, we were talking about electron clouds where we have a probability of an electron occurring. So then let's start to look at those orbital shapes that we saw with Schrodinger's equation. And so here's some of the general ones. Now, for our purposes, I need you to kind of have an idea of the S shape and the P shape. Now, you need to know about the d orbitals and the F eventually. I don't need you to try to memorize those shapes. So S, think sphere. So it's really just a sphere. And the other important thing is that each S orbital can hold 2 electrons before it's full. And again, this has to do with all of the math that was done. And also 2 experiments have shown this all to be correct, at least as the current model. And so once an S orbital has 2 electrons residing within it, again, probability-wise, they're somewhere in that sphere, then you'd have to move on to a different orbital. Each p orbital can hold a total of 6 electrons. And I know at the moment the 3 orbitals is a little bit confusing, but all we mean here is if you look at each one of these are each a configuration for the electron. So each of these is a unique orbital. It's hard to tell, but we're trying to show you 3D space here. And again, probability-wise, we'd expect an electron there and there, 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 and there. Now, at any one moment in time, could both those electrons be on the same side? Sure. Could one of those electrons be somewhere else, kind of not quite within this shape? Of course, but a majority of the time, we're predicting that one electron will reside in each of these lobes. Now, down below, I don't need you to worry about those shapes, but I do need you to realize that the d orbitals are able to hold 10 total electrons. So again, within the d orbital, there's 5 suborbitals, each holding 2 for a total of 10. And I think that'll become a little less confusing as we move into configurations a little bit more throughout the rest of this week. And we do have f orbitals. And again, 7 orbitals that each can hold 2. So the total electrons that can fit into the f orbitals is 14. And again, you're seeing here it's starting to get even weirder in the shapes. And remember that as we're filling into orbitals that are further and further away from the nucleus, they have more and more energy. And so they are residing in odd shapes far away from each other with greater energy. Now, this is theoretical, so you don't need to take this down, but theoretically, g orbitals exist, and actually, theoretically, orbitals continue outward from a nucleus forever. And so, theoretically, if you added enough energy to electrons, they could get into these G orbitals. The thing is, once you start adding enough energy to an electron, it can escape the atom, and it no longer is going to be part of that orbital for that electron, and that creates an ion. So we've talked about ions a little bit. So when an atom loses an electron, if it gets energized to the point where an electron actually just moves so far away that it's gone, we've created a cation because we've lost an electron, and we're going to have an overall positive charge. So then as you start to think about this as well, remember that as we move further away from the nucleus, we have more energy for those electrons. And so the 1s, if you look at its shape versus the 2s, the shape's the same, but the size is different. And that's because at 1s, it is closest to the nucleus. And so those electrons do not have as much energy as the electrons residing in 2s. And that means they're going to be further away. It's also important to realize that the orbitals overlap a bit. And, well, not a bit, they do overlap. You have 1s and 2s. And then you kind of factor in 2p on the edges there. And so what you start to realize is this starts to get messy. And again, it's all probability because they repel each other. We can predict that the electrons would repel each other in a way that they'd fill these 3D shapes. Okay, again, 90-ish% of the time. And you'll see as we really add more and more orbitals in, it gets just to be a complete mess. And so it's very hard to visualize this, and we won't ask you to ever try to visualize it this way. So instead, we still need to talk about how electrons fill in, and that's where we come in with the electron configuration notation. Before we get there, let's just do a quick check-in. As you think about this, these shells are really just orbitals. So first orbital, second orbital, third orbital is the other way to think about that, but shell is kind of an interchangeable term. We know that if you have an electron in the first orbital versus the second, it's not going to be the same. We know that as you move further away from the nucleus, there's greater energy. And so if we're comparing the second orbital, then the first orbital will be lower. And so that is your answer. So then how do we show this electron configuration? Obviously, you cannot try to draw the 3D shapes and show where electrons reside. So instead, we're going to kind of use this configuration. And it's going to look something like that. And we'll learn how to do that. And that really won't be until actually later in the week. We're just introducing you to the concept here. We're going to use coefficients. And so those coefficients are those big numbers out front. And those represent the energy level. And you'll see that in a moment. We're going to use the superscripts to talk about the number of electrons in each of those orbitals. And again, remember that an s orbital can hold 2. And then once you have 2, you have to move on. This s orbital can hold 2. Once it has 2, we got to move on. Now p can hold 6. And so as we're filling in around the nucleus and we want to know where these electrons reside, we need to remind ourselves how many an s and a p and a d and an f can hold. And again, one last time, and I know I've gone through this a lot, but it's important to remember that as your energy level increases, so again, as these coefficients out front increase, those electrons have more energy and are further from the nucleus. So then the final idea is kind of how do we fill in and where are these electrons going as we fill them around the nucleus. So again, you will notice that down here we've got our nucleus, obviously not scale. And again, I'm showing you more of a Bohr model right now just because it's simpler than trying to picture those 3D shapes, even though we know that these orbital clouds and the quantum model is how we picture an atom. And so it just so happens that in the first energy level, we have a single sublevel, and that's 1s. And then in terms of the second energy level, we have 2 sublevels. So we have an s orbital, and then the p orbital is right here. Remember, we said that, like, for example, the p orbital has 3 orbitals, each hold 2 electrons. So that's where the 6 total comes from. Now, in the third energy level, we have a 3s, a 3p, and now a 3b. Again, notice that each of these can hold 2 electrons. And as you recall, we can hold 10 total electrons because each of these orbitals can hold 2. So 5 times 2, we get 10. Fourth, you're probably getting a feel for it. Now we have 4s, 4p, 4d, and 4f. Something to point out, though, notice that our s As we fill in, as we get further from the nucleus, we know that this is increasing in energy. Notice that despite this being 4, as we go up in energy, then it's the 3D, and then we come back into the 4th energy level. And so that's why this gets complicated. If we were just following through numerically, it'd be much easier, but we don't. And it has to do with energy, and it has to do with the repulsion and all these the orbital interactions. The idea of it, remember, theoretically, there's G's at this point. We're not even showing them. And notice that as we do 6 in the 7th energy level, it starts to get really messy. And so we need a good method to understand how do we fill in electrons, where do they reside, so that they're in their least, or I should say their most energetically stable configuration. And so there's a couple ways. Number one, you've got this right here. I call this the yellow brick road because I used to hand it out on a yellow piece of paper. So if you follow the yellow brick road, and here's what I mean, just watch. We're going to be filling in, as we go through, we're filling in least energetic first. So first we have 1s, then we come back up to 2s, then we come to P3s, come back up, follow, there's 3p, and then 4s. So I'm just going down each line in order. And if you follow this yellow brick road, you will get the correct filling order in terms of energy. And we'll stop there. Again, theoretically, we go forever, but hopefully that you get the idea. And we'll have you write this down at some point, this little yellow brick road cheat sheet idea. So that's one way to fill in, as that kind of follows that pattern. So again, we will use this and we'll get it to you at some point. The other way, this is the last thing I'll kind of leave you with, is it's actually built into your periodic table. So we wanted you to interact with the periodic table a little bit. You've labeled some groups, and we'll come back and talk about some of those groups. But what you'll also realize is that the periodic table is built around the idea of the electron configuration. And you'll see there's a number of reasons this all ends up working out. So there's our energy levels, which you originally just labeled as the periods. So 1 through 7, periods are like rows in the periodic table. And what we'll find is if you think about, let's say, an s block or an s orbital, remember we said that each s orbital can hold 1, 2 electrons. And if this yellow right here is the s block, you'll notice that in terms of filling in, as we move through them, it can only hold 2 before you have to move on and go somewhere else. Let's talk about the P. So this right here, all of these are the P block, this entire pink area. And again, remember, P can hold 6 electrons. So 1, 2. Notice that as we go across the P block, we have spots for 6 electrons to fill in. Now, I know there are actual elements there and that the proton, right, atomic number is changing as you move across as well. And we'll put this all together for you, so I don't want you to get too confused here. But just realize that the periodic table, because of its blocking, matches what we just learned about. D block can hold 10. So I'm not going to write it for you, but if you go across here, you can guess there's going to be 10 spots, if you will, to hold those 10 electrons before we move on somewhere else. The F block, and again, F can hold 14. So there are 14 spots along there. So what we'll realize is, based on the organization of the periodic table, we end up getting all our S, P, and D and F blocks laid out perfectly for us. And we can actually use the periodic table. So you can use the periodic table to figure out the fill order. You can also use that orbital, follow the yellow brick road, but you've got options. Now, as we fill in, we need to abide by a couple of principles. There's 3. We're only going to worry about 2 of them. Aufbau says that electrons are going to fill into the lowest energy orbital available. Now remember, an s can only hold 2. So if that s is full, it needs to move to the next available energy orbital, lowest. And so you will get a feel for this. Again, this is utilizing the periodic table to get your fill order. And then Hund's rule is another one to be aware of. Hund says that if you have equal energy orbitals, which I will show you in a moment, each must have 1 electron before it takes in a second one. And so I will show that visually in a moment. So those are the main two. Poly as well has a principle. We're not going to worry about it, so do not worry about that. So let me show you these real quick, and we'll wrap things up. The off-balance principle says that we fill into the lowest energy orbitals first, and the way to think about this really is to follow the Elbrick road. That gives you the least energetic first. The other way to think about this is the lazy tenant rule. And so let's say this is a weird-looking apartment complex, and it does not have an elevator, and I am lazy and I'm moving into it. If the 1S is available on that first floor, I'm going to move in because I don't want to have to walk up a bunch of stairs. Now, if the 1S is occupied, I would next go to the 2S. It's not as close to, the ground level, but it's less stairs than randomly, going up somewhere here. If the 2S isn't available, then I could move to the 2P. It's a little higher up, so I'd have to exert a little more energy, but you get the idea. We fill into the lowest energy possible first. The Hund's rule, which again, with a sublevel, you want to put electrons into empty orbitals first. And so let's say in my 2p, so that's what I mean by within a sublevel, let's say it's 2p, I have 4 electrons to place. I could place them like this, or I could place them like this. According to Hund's rule, we place them like we do on the right. So notice that there's an empty orbital right here where an electron could have gone. And so we need to fill in the empties first. And this has to do with the idea that they repel. Electrons repel each other, so they're going to spread out before they pair up. The other way to think about this is kind of like the empty bus seat rule. So if you were to get on a bus and there's one other person on there, and remember, electrons repel each other, so let's say you do not like this person, you're not going to go and sit right next to them. You're going to probably fill out away from them, and that's the idea of Hund's rule. So the last thing I'll leave you with is as we move into the second part of this week, we're going to start to get used to filling in electrons and kind of using this pattern on the periodic table. So there's a number of really interesting trends that pop up in the periodic table, but kind of a main one is this configuration that kind of matches as we move through the periodic table. They're filling in according to the off-balance principle. That's it. This is just an introduction to electron configuration. We will learn a lot more about that and practice it later in the week.